Hi, this is Rick for EDU Mobile. Now we're going to look at structures in Swift. Structures are very powerful in Swift, and they give us an opportunity to do things that we weren't able to do in Objective-C or other languages that use structures before. A structure in Swift, as we already know, can house methods to operate on its members, or even have type methods, what we used to call class methods, to operate on the structure instance itself. So here we go. I have modeled a complex number. It turns out that mathematical modeling, things like points, lines, planes, complex numbers, for instance, matrices, vectors, things like that that we use in computation, are in Swift best modeled as structs. Why? Because they're value types. They're not instance types. We don't have to worry about allocation and deallocation. Value types kept on the stack. And when they're no longer used, they're there. When the program ends, when the application stops, they go away. So not garbage collected or anything like that. So here we have a complex number. Complex number has a real part and an imaginary part. Now, we have not initialized real part or imaginary part. We've made these both doubles. But since we've not initialized them in their declaration, we need to do so in an initializer. Remember that if we don't initialize a property, these are stored properties, if we don't initialize a property, we need to initialize it in an init. So we need at least a no argument init method. This is the initializer. Here in our no arg initializer, we set real part and imaginary part both to 0.0. We have to say 0.0 because they're doubles. If we just say 0, we'll get a conflict about assigning. Actually, no, we won't. Never mind that. We also want an initializer that sets real part and imaginary part to actual numbers. So we pass in real and imaginary. And these are both doubles, and of course then we just set real to real part and imaginary to imaginary part. Now notice that we don't have to use self in these initializers. In the second initializer, real and imaginary, the parameter names, are not the same as the names of the stored properties. If they were, then we would have to distinguish between them by saying self.realPart and self.imaginaryPart. But normally we don't have to use self. Now we also have a function here called PrettyPrint. PrettyPrint will print out the complex number in this form. It'll print the real part and then the imaginary part. And it will also correct the sign if the imaginary part is negative. So if the imaginary part is negative, we want to have real part minus the positive value of the imaginary part. Otherwise, we want to have real part plus. We don't want to have something like 3.3 plus negative 2.4i. So there we go. And it's just PrettyPrint, a pretty standard name, fairly standard name for something that prints out something in a formatted way. Now, I also have a couple of type methods here. I've declared these add and multiply. I should first talk about parameter names and initializers. If we have an init method, notice this isn't init with real and imaginary or something like that. Init methods are always called init. They are distinguished by their parameter lists. So in this method, we must use both parameters. In init methods, both of these parameters are external parameter names. So when we call this method, we need to call it as init real and then the value, imaginary and then the value. But with normal methods, even type methods, the first parameter is not externalized, but all others are. So here in our function add, when we call this, it actually reads add this number to this number. And that's why I've named this parameter 2. This is an external parameter name. This, by default, again, is not. So in the add method, we add two complex numbers. We add their real parts and we add their imaginary parts. And we return a new complex number. This is a type method because it doesn't deal with our complex number as it is here. We could set up an add and then just add a new complex number to the existing complex number. We certainly should do that as an exercise, hint, hint, hint. But in this case, we're just adding two complex numbers, presumably that we've already set up someplace else. Notice that we can use the type name here. The type is complex. It's assuming that we're going to get a complex number and another complex number, add their real parts, add their imaginary parts, and return C. Notice internally, since this is externalized and it's also the internal parameter name, I use 2 for the second imaginary number. The multiply method returns the product of two complex numbers. Since the final term of the product of two complex numbers is something I squared, that can just go back into the real part. As long as we preserve the sign where the I squared is of course -1, we must multiply the product of the imaginary parts. The second term is going to be the real part times the imaginary part, and then the imaginary part times the real part, and it will be the sum of those. So we return C again. So now that we've defined our structure, and notice that these functions, since they're type functions, are declared with the keyword static, we have two instances of a complex number. We have test1 and test2. Real, imaginary, real, imaginary. Now, again, with the initializers, we initialize them using both parameter names since both of them are externalized. Now we want to print them out, PrettyPrint them. So we have 3 and -2.4. It comes out as 3.3 minus 2.4i. And then we have 2.4 and 3.4, and it comes out as 2.4 plus 3.4i. Now we add them. So let sum equal complex add, and we're adding test1 to test2, and then PrettyPrint sum. So we get 5.7 plus 1.0i. If we multiply them, we have product equal complex multiply test with. So look at the names of the functions as we call them. We have add test1 to test2. We have multiply test1 with test2. So this makes sense. This is good. This externalization of the second and subsequent parameter names is very good with methods because it allows us to make our methods or name our methods like we would in Objective-C. So we PrettyPrint the product and we get the right product. Now, these let structures are immutable. Notice that up here I've declared real part and imaginary part to be vars. Those are mutable, but an entire let structure is immutable. If we try to change, for example, test1's real part, we get an error because test1 was a let. To correct that, we might make test1 a var, and now this will work. And the error went away. But I like it as a let. So we'll keep it that way, and then we'll just comment this out again. All right, so now we're going to make a var test3 and just copy test1. Value types, when we copy them, copy the value, but not the instance. It's not a deep copy, it's a shallow copy. And test3 is a mutable copy in this case because we've declared it as a var. If we print out test3, we have real part, imaginary part, and if we say test3 dot PrettyPrint, we get the same complex number as test1. If we change a value in test3, since this is a var parameter, it's mutable. Since it's a var value, it's mutable. If we change a value in test3, it shouldn't alter test1. because structures, again, are value types that are shallow copied. So test3 real part is 4.26, but if we PrettyPrint test1, we'll see that the real part of test1 didn't change. So again, mutable value types, when they're copied, or copied as mutable types, we can change a value and it doesn't alter the value of the copied value type. All right, so some of the things that we can do with structures. We've also covered some of the things that we can do with classes, such as type methods, static methods, and we have begun to examine the properties, stored properties here certainly, and methods and initializers that apply to both structures and classes. Thank you very much.